So here A is 1, 2, 3, 4, 5, 6. And I is a 3 by 3 matrix. So we can see that this I and this I are different, right? Because here we multiply I with A. So I is the first matrix, but here I is the second matrix. So we should use different dimension of I. But the results are the same, right? We can calculate that. So here, because of 2 by 3, right? So the first element here should be using first row here and first column. And then second element here should be first row and second column. And the first row and the third column. Right? When we calculate, we can see that, for example, when we calculate the first row and first column, because the 2 here are 0, right? So when we calculate 2 times 0 and 3 times 0, the results are 0. So here's 1. So the only remaining non-zero element here is 1 times 1, right? So we have 1 here, and all the other 2 are 0. And when we calculate the second element, the first position and the third position are 0. So 1 and 3 are cancelled. So only the second position, which is 2, is 1 here. So 1 times 0 plus 2 times 1 plus 3 times 0. The result is the second element here. Only the second element remains. Right, so we can see that because there are a lot of zeros here, so when calculating the inner products of them, some of the elements are cancelled out, and only the position with 1 remains in our calculation. So here we have 4 remains, and then 5, and then 6, and all the others are 0. So the resulting matrix is still 1, 2, 3, 4, 5, 6. Is equal to these matrices, right? So these two results are the same. So we can see that no matter you use what kind of dimension of identity matrix, the results are the same. The A times I or I times A is just the matrix A itself. So the identity matrix is just like the number 1. Right? Although we have to use different dimension of I when we calculate it. So here are some notes. First, A times I times B. So A and B are just any kind of matrices equals to, you calculate A times I first and then times B. Right? But it's also equal to A times the result of I times B. Right? In either way, because A times I is just A itself, and I times B just B itself. Right? So the results should be A times B. So we can just cancel this I here, and the result is A times B. Like we cancel the number 1 when we are doing the multiplication using numbers. And second, if A matrix is just the identity matrix itself, then A times I is just I times I, right, with any dimension n, I times I. And we know that the identity matrix times any kind of matrix A should be the matrix A itself, right? So the identity matrix IM times IM itself should also be IN, right? And is called IN squared, but the result should be IN itself, right? Or IM times IN times IN, or times, anyway, times infinite number of IN, the result should also be IN. We cannot change that. Right. So this is another property. So IM, or the identity matrix of power k, that means you times the identity matrix k times, for example, this k times And the result should also be the identity matrix itself. And the third one, the identity matrix, is idempotent. So this means if matrix A times a matrix A equals to the matrix A itself, then this kind of matrix we call the idempotent. Right? The multiplication of the two same matrices results to the matrix itself. So this is a kind of property that the identity matrix has. Because we've talked about it before, I times I is just I itself, right? If you want to calculate that yourself, so for example, let's find a place here. For example, if we calculate I3 times I3, right? The first, we have to times I3 with I3. You cannot times I3 with I4 or 5, right? Because they're not conformable. I3 times I3. So this should be 1 0 0 0 1 0 0 0 1 times 1 0 0 0 1 0 0 0 1. Right. So the first element, so the resulting matrix should also be 3 by 3, right? So first we calculate the first row and the first column. So that's 1, right? Because this is 1 times 1 plus 0 plus 0. So only 1 left. And second, we calculate first row, second column, right? So first row, second column is 1 times 0, 0 times 1, 0 times 0. So all of them are 0. So the 0. And then we calculate first row and the third column. So that's 1 times 0 plus 0 times 0 plus 0 times 1. So that's also 0. And second row, first column, that's 0 times 1 plus 1 times 0 plus 0 plus times 0. So it's 0. And then 0 times 0 plus 1 times 1 plus 0 times 0. So that's 1, right? And then this is 0, and we can find that this is 0, 0, and 1 left, because the last element is to use the third row and the third column. So 0, 0, and then 1 times 1, so that's 1 here. So the resulting matrix is still the same as I3, right? So that's this property. It's idempotent. Okay, so this is identity matrix. We can consider that to be of number 1, as we learned that before. And you times any kind of matrix with the identity matrix. It's the matrix itself, right? And but when you multiply the identity matrix and before that or after that, you have to change the dimension of it, right? Okay, so this is identity matrix. And then we'll talk about the null matrices. So null matrices are very simple. It's just all the elements here are 0. And the null matrices, they don't have to be square matrix as the identity matrix does, right? So here when we talk about the identity matrix, we say that, okay, they have to be a square matrix. Sorry, they have to be square matrix. But for the null matrices, they don't have to be square matrix. They can be of any dimension. For example, we use 0 to represent the null matrices. If it's 3 by 3, that means that all the elements here are 0. So we have 9 0 here. And if it's 2 by 3 null matrix, then it's a 2 by 3. We have 6 zeros here in the matrix. I mean, all the elements here are 0, and they don't have to be square matrix. So this is null matrices. And we have some properties here. First, any matrix A plus the null matrix should be the same when you change the order, and it should be the matrix A itself. But pay attention that the null matrix has to be the same dimension of matrix A, right? Because we're doing addition here, matrix addition here. So A and the null matrix have to have the same dimension in order to be added together, right? So the null matrix is like the number 0, right? So 2 plus 0 equals to 0 plus 2 equals to 2 itself, right? So this is in the number algebra. But you can consider the null matrix as the number 0 in the matrix form, right? Any matrix plus a 0 matrix is just the matrix itself. And any matrix A times a conformable null matrix should be the null matrix, should be another null matrix, right? Just like 2 times 0 equals to 0, right, in the number algebra. But pay attention that here, the null matrices have the different dimension, right? Just like the identity matrix before we talked about that. So if A is n by n, then the conformable null matrices to do multiplication is of dimension n by something, right? Because we have to keep the two numbers here the same. So let's say it's n by p. And the resulting matrix should be of dimension n by p, right? So this matrix is n by p, but here it becomes n by p matrix. Although both of them are called null matrices, but they have the different dimension. So they are not the same matrix, right? They belong to the same class, null matrices, but they are considered to be different matrices. And then again, if you multiply a null matrix with A, we have to make sure that the column vector here is the same as the row vector here, a row dimension here, so both of them are n. And so this Q is just an arbitrary number, but we have to make sure the n is here, right? The same as the n here. So let's say it's Q by m, and Q by m times a n by m matrix. The resulting matrix should be a Q by m matrix. So again, the dimension of the matrix here is different from the dimension of the matrix here. Although both of them are called null matrices, but they are different matrices because they have different dimensions, right? They belong to the same class, but they are considered to be different matrices. Okay, let's see some example. Again, A is 1, 2, 3, 4, 5, 6. It's a 2 by 3 matrix. And the null matrix that's conformable should be of dimension 3 times something, right? So we just say it's 3 by 1. So if 3 by 1, then it's a column vector, and all the elements here are 0. And the results should be a 2 by 1 matrix, right? A 2 by 1 matrix. So we calculate the first row and first column here. We see that 1 times 0 plus 2 times 0 plus 3 times 0. The results clearly is 0. And again, we use the second row times the first column, which is only column. So there should be 4 times 0 plus 5 times 0 plus 6 times 0. So results again, 0. So the result is a 2x1 null matrix. But here we use a 3x1 matrix to do the multiplication, and the result is a 2x1 null matrix. So they are different. Although both of them are called null matrices, but they are different. Right. And we have some notes. First is A times B is 0. So if A times B equals to 0, then it doesn't necessarily mean that A or B is the null matrices. So this should be null matrices. If A times B is a null matrix, then it doesn't necessarily mean that A or B is the null matrices. So for example, so A and B are like this. Both of them are 2x2 square matrix, and none of them is null matrix. But the multiplication of A and B is a null matrix. We can calculate A times B. Because A is 2x2, B is 2x2. So the resulting matrix should also be a 2x2 matrix. And the first element is we can use the first row and the first column, right? We calculate 2 times minus 2 plus 4 times 1. So that's minus 4 plus 4, right? So this is 0. And then we use the first row and the second column to calculate. So that's 2 times 4 plus 4 times minus 2. So that's 8 minus 8. So that's again 0. And then we use the second row and the first column. So that's 1 times minus 2 plus 2 times 1. So that's minus 2 plus 2. Again, 0. And then last one, 1 times 4 plus 2 times minus 2. So that's 4 minus 4, right? So again, 0. So the result is a 2x2 null matrix. Although neither A nor B is a null matrix, but the result is a 2x2 null matrix. Right? So A times B equals to null matrix. It doesn't necessarily mean that A or B or one of them or both of them is a null matrix. So this is different from the number algebra. Right? In the number algebra, we said that the number A times number B equals to 0. So that means that A or B is 0. Right? But this is not true in the matrix algebra. Okay. So the second one is matrix C times matrix A equals to C times B. And matrix C is not the null matrix. Right? The matrix C is not the null matrix. If this equation holds, then it doesn't necessarily mean that A is equal to B. Right? So in the number algebra, so if the number C times A equals to number C times B, if C is not 0, then the only reason for this equation to hold is that A has to equal to B. Right? But this is in the number algebra, but in matrix algebra, this is not true. Right? Even though C times A equals to C times B, and C is not a null matrix, but it doesn't necessarily mean that matrix A is just a matrix B, the same. Right? So here are some of the differences between the number algebra and the matrix algebra. Right? In matrix algebra, because in a single matrix, we have a lot of numbers, a lot of elements. So it's a little bit more complicated to do operations as we did in the number algebra. Right? So even though the identity matrix and null matrices are kind of like number 1 and number 0 when we learned in the number algebra, but they have some differences, right? Because they're matrices, they're not numbers. So you have to pay attention to that. Okay, so this is the null matrices. And then we'll talk about the transpose and inverses. So first, transpose means the rows and the columns of the matrix are interchanged. Right? And the transpose of matrix A is written as A prime or A to the T. Right? Here's a T, means transpose. But most people prefer to use A prime, I think. And so for example, let's see an example. Right? So if A is a 2 by 3 matrix, so A prime or transpose means we change the rows and columns of a matrix. So it's kind of like we flip the matrix of A, the matrix A, and we change the 2 by 3 matrix to a 3 by 2 matrix. So the elements, they don't change, right? They don't change the exact elements, but they change the positions of the original elements in matrix A. They change the positions of the elements to a new position in A prime. So specifically, so here in general, so if A is here, so all the little a's, so small a's here, they're just a number, right? So when we write out the A prime here, it's kind of like we flip the matrix A along this diagonal. Anyway, let's see. So the original A11, the first matrix in the matrix A, is again the first matrix in the matrix A prime. But the original A12 here, it lies in here, right? So here, this is the second row and the first column of the matrix A prime. And here, A12 lies in the first row and the second column. So we can see that the position of the rows and columns are interchanged, right? So A12 here is in the first row and the second column of the matrix A. But if we transpose the matrix A, the A12 here becomes the element of the second row and the first column, right? So if we write out the position of A2 prime, maybe that's a little bit complicated. So all the small a prime here means the position of the elements in the A prime, right? So we can see that the original A12 here becomes the position A21 prime, right? The rows and columns 1 and 2 are interchanged to 2, 1, from 1, 2 to 2, 1. So this element here becomes the second row and the first column element. And A13 here, it lies in the first row and the third column. And if we transpose that, it becomes the third row and the first column. See, the position of the row and column are changed from A13 to A31 prime. But it's the same number, but in different position, right? Back to this example. So we can see that 3 is A11, right? In the position A11, first row and first column. So if we change the row and the column, it's still 1 and 1, right? This is A11. So the number of the row is 1, number of column is 1. So when we transpose that, it's still the first row and the first column. So the 3 here. But for the 7, it's in the first row and second column, right? It's A1, 2. So if we transpose that, it becomes A21 prime because it's in a new matrix called A prime. So 7 should lie in the second row and the first column, right? Not the first row and the second column. And 6 here is in the first row and the third column. And if we transpose that, it becomes the third row and the first column, right? Becomes A31 prime. Right? So we can see that we changed the position of the original elements, and we change the number, the position of the row and position of the column of the matrix, right? It's kind of like we flip the matrix through this diagonal, right? And again, for the second row and the first column, the number 1 here, it becomes the first row and the second column, right? And number 4, second row and the second column, we transpose that, it becomes the second row, second column, right? The position doesn't change. And for the 5 here, it's in the second row, third column. So when we transpose that, it should become the element in the third row and the second column. Right. So we interchange the original position, the row and the column position, and we interchange the position of them. So A23 becomes A32. A22 is the same. A21 becomes a new A12 prime. Okay. So here another example for matrix B is 1, 2, 3, 4. So B prime is 1, 3, 2, 4, right? So it's if it's a square matrix, it's clear that it's just like you flip the matrix B through this diagonal, right? From this diagonal. So 1 and 4 because they lie in a diagonal. So the position doesn't change, right? Because this is in the first row, first column. So when transpose that, it's still in the first row, first column. So 2 is in the first row and second column. So when I transpose that, it becomes the second row and the first column, right? We interchange the position of the rows and column. So to be more specific, if the original element is Aij, right? So I is a row, J is a column number, and the new element position in the transpose matrix should be Aj. Right? We interchange the position of row and column from Aij to Ajui prime. We don't change the element, just change the position, right? So this is called transpose. And here we have another definition. It's called symmetric matrix. Symmetric matrix means when you transpose the matrix, it's just the same matrix as before, right? So this kind of matrix is symmetric. Let's see an example. D is 1, 2, 3, 2, 4, 5, 3, 4, 5, 7. The 3, 5, 7. As I said, to transpose, it's kind of like you flip the matrix from this diagonal. So we can see that it's symmetric, right, from this diagonal. And its 2 is symmetric to this 2, 3 is symmetric to this 3, 5 is symmetric to this 5, right? So it's symmetric matrix. And if we transpose that, so the elements in the diagonal, they don't change the position. And for the 2 here, it's the first row, second column. So now this 2 becomes this 2, right? The second row, first column. And this 3 becomes this 3, right? From the first row, third column becomes the third row, first column, right? And so this 2 becomes this 2, you flip that. This 3 becomes this 3, again, you flip that. But we can see that the resulting matrix D prime is the same as the matrix D. Because when you do the flip, it's just symmetric to each other, right? The upper part and the lower part are symmetric to each other, so you don't change the original matrix. So D prime is just a D. Okay, and here are some of the properties. First is that A prime and then prime, right? 2 primes, it's just A itself. That means that when you transpose a matrix A and then transpose back, it means that you flip this matrix and then flip back. Then it's just the original matrix. You don't change the matrix. You change the position and then change back. So it's just the original matrix itself. And then second, A plus B and then prime is just A prime plus B prime. Right. So the third one is A times B and then prime and the transpose is B transpose times A transpose. So we change the position from AB to BA. So let's see an example here. We have A and B. First, we calculate A plus B and then prime. So A times B and then transpose. A plus B. A plus B is this matrix. And then we take the transpose. It's like we flip the matrix. It's a square matrix, so it's very easy to see the transpose result. It's 1, 9, 1, 11. Right? We interchange the 1 and 9 here. And the diagonal matrix, the diagonal elements don't change. So this is a transpose result of A plus B. And we can calculate A transpose plus B transpose. So A transpose, we interchange the position of the elements here. So 1, 2, 3, 4, it becomes 1, 4, they don't change, and 2, 3, they change the position, right? And the B matrix is 0, minus 1, 6, 7, because the square matrix again. So 0 and 7, they don't change. And the minus 1 and 6, they change the position, right? And then we calculate the addition and we find that, okay, these two things are equal to each other. So A plus B, the summation of A plus B and then prime is just equal to A prime plus B prime. And we calculate A times B and then transpose. So A times B, I can skip the calculating process here. A times B is this thing, right? And then we calculate the transpose of this matrix. So it should be, again, 12, 25, 13, and 24, right? We interchange the position of 13 from 1, 2 to 2, 1. And 24 is 1, 2, 2, 1. So here it becomes 1, 2. Sorry, from 2, 1 to 1, 2. So that's 24. So this is the result of the A times B and the transpose. And then we calculate B transpose times A transpose. So B transpose, as I said, is 0, 6 minus 1, 7. A transpose is 1, 3, 2, 4, right? And then you calculate this and you find that it's the same matrix as A times B transpose. So just pay attention that when you calculate the product of A times B and the transpose, it's not equal to A transpose times B transpose, right? You have to change the order. we have to change the order from AB to BA, and both of them transpose and then times together, right? So and multiply together, right? So this is sometimes confusing, but you have to remember that clearly. So this is some of the properties of the transpose.